So myself, Amrit Sahu. Okay, so this is kind of an introductory course to combustion concepts. We'll be going stage by stage as we go through this GYAN program, right? So a brief background about myself. So basically, I finished my BTech in mechanical from NIT Rourkela. After that, I did my PhD at IISc Bangalore, and following that, I have postdoc experiences at University of Birmingham and University of Ireland Galway, where I've worked on combustion kinetic mechanism developments, right? And after that, I had an opportunity to even work with some startups in the US, where I was mainly focused on developing compact combustors. Okay. Post that, I joined IIT Bhubaneswar. It has been over 2 years now, where I think you guys visited one of the labs yesterday. So the areas of research what we work on is focused on future fuels, clean combustion technologies, but also we are looking at hydrogen safety, hydrogen storage safety applications, right? And some of our work is also focused on the optical diagnostics for thermofluid applications. I think you saw some interferometry experiments yesterday, so that is one of the areas. And we are also working on developing low-cost, low-order computational models, so that which you can use for CFD simulations for practical combustors, right? So with that, so first let's get started with where do we see combustion in real life, right? And it is pretty common to us. So you see in the automotive sector, right? Your passenger cars, heavy earth movers, as well as marine sector. Okay, all of these employ some kind of internal combustion engine, correct? With various geometries using different types of fuels, but all of them use combustion as the power generation mode, right? The second one is for stationary power generation. Your thermal power plants also use coal-fired, natural gas-fired furnaces to boil waters and create steam and generate power out of it. And again, like in domestic applications, all your cook stoves basically have some kind of combustion going on. That also converts your chemical energy into thermal energy, which you then use for cooking and other applications. And also we have your entertainment purposes, all your pyrotechniques also employ some form of combustion, right? So these are combustion. What we mean is these are designed, engineered devices which basically harness that energy, control that combustion process so that you extract useful work out of it. Okay. However, we come across these kind of incidents also, like natural calamities like wildlife, forest fires, then apartment fires. I think yesterday we saw a lot of these from our speakers, and these are growing day by day. All right, so this was early 2025. We have California wildfires, which basically created a huge loss to our losses in life and property. And very recently we had, probably in the past 3-4 weeks, we had 2 incidents. One is the apartment complex fire in Hong Kong, right? That was 3-4 weeks back, and then this Goa nightclub fire, which just happened 2 weeks back. So all of this, what it determines is we are living in a society which is surrounded by combustible materials, and which accidents can happen. Even if you take proper precautions, accidents can happen, and these kind of calamities will happen. So to understand these phenomena, we still call it as fires, not flame. Can anyone distinguish between a flame and a fire? So we call these as fires, right? However, do we call this as fire? Like when you light up the stove, do we call it fire? So, yes?
Generally we call uncontrolled combustion is as a fire.
Uncontrolled combustion is fire. Right. So uncontrolled combustion, these are, how do you control these flames? So what is the mode of control here?
In gas stoves we have a regulator.
You have a regulator.
So control.
So it is controlled. So one way of controlling is you are controlling the flow rate of the fuel that is being fed to the gas stove. Great. So one of the key distinction between when you call a flame and fire is, fire basically represents uncontrolled combustion which is basically expanding. Okay, but however, in technical terms, we still can classify these as flames, as non-premix flame or diffusion flame. We can study those, apply those physics that we see in the controlled flames to understand the fire hazards that we are seeing. Okay, so even though they are uncontrolled, but the physics that goes behind this is still the same. Okay, so this is something that we all know, right? This is a combustion triangle. So you need fuel, oxidizer, and some kind of an ignition energy or some kind of heat transfer to have a combustion successfully happening. All right. So on this right hand side, these are basically small combustor cavities, transparent combustor cavities, and what we have is a spark plug that basically gives the ignition energy, and you can see the flame front propagating, right? And these are basically captured using high-speed cameras at probably 4,000 frames per second. So that is why you can see the flame propagating in real life. But you can see the time that it takes. These are milliseconds. So 20 milliseconds, the combustion process is done, right? So we use this kind of diagnostics to visualize how the flame front is propagating. Now, is this a sufficient condition to have combustion? Yes, no, yeah, you can interact, yes.
So fire triangle is mainly used for ignite the fire, but for continue it is need of redox chain reaction.
Okay, so can you ignite the fire by just having fuel and oxidizer, or do you need something else?
It is initial energy, it is used for ignite the fire.
Okay,
Or if we can so say it is a heat.
okay, alright. Anyone? Please sit. Thank you. So you have fuel and oxidizer and you just ignite it, you provide the ignition energy, will it ignite? Even if it is not sustained? It may not ignite. Okay, so what is important is, so in this chamber, before we trigger the spark plug, let me just pause here. So there are various steps that we had to do. So we had to basically fill this chamber with a certain ratio of fuel and oxidizer. Okay, that falls within the flammability limit. Alright, so if you have, depending on the fuel and oxidizer, if you have 90% of fuel and 10% of oxidizer, and that is beyond the flammability limit, then even if you provide the ignition energy, it will not create this kind of a flame front. Okay, so you will not be able to sustain this flame. So what happens is, first we basically create a homogeneous mixture of fuel and oxidizer inside this chamber. Okay, so for a particular equivalence ratio, and then we get the needed ignition energy through this spark. Using that, through that, we are able to sustain a flame front. So you can see this circular surface is basically the flame front, and it basically propagates through the medium. Okay. So now what is going on? So how is the flame propagating? So why is this flame front propagating through the medium? So we are supplying the ignition energy at the spark, right? So here it has not received any ignition energy. So what is happening? It will take time. Okay. So, but what is the mechanism? What is the mechanism of this gas getting ignited? So we have the spark at the top, right? And you see the flame slowly propagating, right? What could be happening?
So oxygen that diffuse into that flame zone area, so that
Oxygen is, so okay, so to start with, we have filled everything with homogeneous fuel air mixture, so the composition is homogeneous, right? So what happens is, so in this region, at this point, you have your fuel and oxidizer mixed in a proper ratio, okay? Now at this flame front, what is going on at the flame front? Correct. So there is some heat that is being generated. How is it being generated? Due to some chemical reactions that are going on, right? Some exothermic chemical reactions that are going on. It is locally releasing the heat, so that preheats this guy, Okay, the fuel air mixture that is sitting very close to the flame front. So once it receives that heat from the flame front, then this zone ignites and you see the flame front propagating. Okay, so the mechanism of, in basic terms, the mechanism of flame propagation is basically you have a heat source term. In this case, this is the combustion zone where your exothermic reactions are taking place at a very fast rate. So that heat is being transferred to the fresh fuel air mixture. Okay, so that is preheating this fuel air mixture, and then this zone ignites. Okay, and it happens at such a fast rate that you see this flame front propagating through high speed imaging. Alright. So now to see, so what is the challenge of this combustion science is, it has three kinds of phenomena that is going on parallelly. Okay, so you have fluid mechanics. So fluid mechanics is basically how you are flowing your fuel or oxidizer into the combustor zone or into your test area, right? Then you have transport phenomena. So what is transport phenomena? That basically deals with the mixing of fuel and oxidizer. So if you just supply fuel and oxidizer in silo, it will not react. So they have to mix and they have to interact at molecular level, right? So that is the next thing. But the transport phenomena basically means that your fuel and oxidizer are mixing with each other, okay? And the next one is chemical reactions. So once they mix and they get the sufficient amount of heat source, energy source, then they will react exothermically to release the heat. Okay, so we have three forms of physics that is going on. One is fluid mechanics, one is transport phenomena, the other is chemical reactions. So three branches of science that basically takes place during this phenomena. Now in this transport phenomena, you don't only have the fuel air mixing, you also have, as we said, discussed, you also have heat transfer going on, right? So a heat transfer or a thermal transfer is going on from this high temperature flame front to the cold fuel air mixture. So there is also energy transfer that is taking place, right? So heat and mass transfer both are taking place in this. So this is one challenge. So it is not one stream that you can focus and understand. You have to understand all these three aspects. The second aspect is these are multi scales, right? The length scales at which these phenomena are occurring are different. So what do you mean by that? When we say fluid mechanics or flow of fuel air mixture, so imagine that okay, so let's say this is our test area. So you are supplying some fuel and oxidizer to this test area, right? So you have to supply fuel and oxidizer mixture, and the flow is happening at a length scale that is similar to the size of your reactor, right? So these are your flow length scales, right? These are observable, like millimeters, centimeters length scales, right? Now when you look at mixing happens at a smaller length scale, right? So the fuel and oxidizer might be mixing at a locally smaller zone, okay, compared to the actual length scale of the combustor or the reactor, okay? So these two length scales are different. Now when you look at reaction length scales, these are basically interaction between, so when you look at reaction length scale, these are interaction of fuel and oxidizer molecules at molecular level, right? So the molecules of fuel and oxidizer, they are basically colliding with each other, and that is taking place at molecular length scales. So those length scales are way narrower than, smaller than the mixing length scale and the flow length scales. Okay, so when you are trying to build a CFD model or resolve these governing equations, you actually have to look at these different length scales and handle them simultaneously. Okay, to successfully simulate your combustion process accurately. So yesterday Professor Kumar was showing some simulations, right, about the fire. So those kind of things you have to look at the wind transfer, the wind gusts that were going on through the windows. So those are flow length scales, right? Then mixing, when the air comes, it has to mix with the fuel that is coming out, combustible metal that is coming out, and then you have reactions going on. which is happening at a molecular level. So you can imagine the range of length scales that you have to resolve. And also then you have time scales. So the rate at which this fuel and oxidizer interact is different than the rate at which you are supplying the fuel and oxidizer, right, through convection. So all these three aspects basically make this study of combustion very, very difficult, right? So you can see this kind of a flame propagation. Again, this is not a very nice flame, so you can see the turbulence and it is propagating in a random manner, right? So this is kind of a turbulent flame propagation that you see. Alright, so these are again taken with high-speed cameras so that you can basically characterize the how the flame is growing. Okay, so to understand these concepts and to basically engineer devices where you can control combustion, you have to basically have a good idea about these three aspects. Okay, so you can have, in some cases, you can have fluid mechanics and chemical reactions taking the charge. In some cases, you can have the mixing and chemical reactions taking charge. But in either of the cases, chemical reactions are something that are going to be critical in a combustion process. And what kind of chemical processes are those? Those are fast exothermic reactions that are taking place. Yes?
What about the pressure?
The pressure will be there. So the pressure is going to affect, so pressure can affect your reaction time scale. So the rate at which your molecules are interacting, fuel and oxidizer molecules are interacting, will be affected by the pressure because the concentration of molecules will increase. That can also affect your flow time scales, right? So if you have a high pressure gradient, right? If you have a high differential pressure, then the flow rates are high. Okay, so and that can affect your mixing and as well as like through reaction. So depending on the type of system, it can either promote combustion or as well as inhibit combustion in some aspects. Okay. Alright. So those are the challenges. Now let's come into, like we understood that chemical reactions are something that is very, very important to understand combustion. So so we all know this stoichiometric air fuel ratio. So that is the minimum amount of oxidizer that you need to basically completely burn 1 unit amount of fuel. So if you have methane and this is your composition of air, right? So you need 2 moles of O2, 7.5 2 moles of N2. That gives you complete combustion products. Okay, and so based on that, so this proportion is called your stoichiometric ratio. In relative to this, if you have excess air, so instead of like 2 into 2 moles of O2, if you have excess air, so you are going to have air as some of the byproducts, combustion products that you are seeing that will be unutilized. In those kind of cases, we basically call it to be fuel lean, right? So fuel is the limiting component. And in the other extreme where you have rich, so you have excess of fuel, so on the product side you are basically going to see unburnt fuel and the intermediate species that will come up, and those kind of mixtures are called rich mixtures. So a term that we widely use in our community is the equivalence ratio, right? So equivalence ratio can be basically calculated as it should be equivalence ratio, not percentage stoichiometric air. So it is basically the stoichiometric air fuel ratio divided by the actual air fuel ratio of your system. So the stoichiometric air fuel ratio basically depends on what is the fuel and what is the oxidizer. Okay. In some scenarios, you may not have air as the oxidizer, you might have enriched oxygen air, enriched air, so where the proportion of O2 and N2 are different. And in some systems, you also have oxycombustion, so where basically you might have a very large amount of oxygen that is burning the fuel. Okay, so in that case, your stoichiometric composition or ratio is going to change. Okay, so there are other ways of also denoting this. Sometimes we call as percentage of stoichiometric air. So for if this kind of value is given, then you can basically find phi as 100% by the percentage that is given. Okay, so you can determine the equivalence ratio in that manner. And sometimes you are given as percentage of excess air. Then you can use, so if you know the equivalence ratio, you can calculate what is the percentage of excess air in relation to the stoichiometric composition. Okay. Now, once we know how to write the appropriate equations for a fuel air mixture, we want to find out what is the energy content of a fuel. So how much heat it is going to generate if we burn the fuel, right? So that is an important aspect. So to do that, we basically want to understand the term that is absolute enthalpy. Anyone? Like what is enthalpy?
Heat content.
Heat content. Okay. To do what?
Heat content in any substance.
In any substance. Okay. So, right. To be more precise, so let's say you have certain amount of gas. Okay. Some fuel or oxidizer. It could be anything. Okay. And the amount of energy that is required to basically form that species at standard reference conditions, right? Reference conditions means your temperature and pressures are basically at 298.15 Kelvin, okay, standard reference temperature, and reference pressure is 1 atmospheric pressure. So the amount of energy that is required to form that chemical species, let's say CH4, it does not exist by itself, right? There is a carbon, there is a hydrogen, both of them form some kind of chemical bonds, and then they form that methane molecule. So that is called as your enthalpy of formation, okay, at standard reference conditions. Now imagine that this methane molecule is also occupying some space, right? So you have to create a space for that methane molecule in your environment, right? So it has to displace the other molecules as well. So you need some additional energy for that, right? So these two components basically will add up and give you the enthalpy term, okay? So just to form the molecules, okay, it could be called as the internal energy, and on top of that, addition of this excess work, that the displacement work that it has to do to like create a volume for itself, that when you add it up, then you get the enthalpy, okay? So now once you form that species and give that volume in your environment, you call it as enthalpy of formation. And then if you are preheating, if you are, let's say your gas is at a higher temperature, then also you have additional enthalpy that is added, that is called your sensible enthalpy. So that is the amount of energy that you need to raise the temperature to the desired, raise the species to the desired temperature. Alright. So the expression is, so the total enthalpy or the absolute enthalpy of any species I, okay, at a desired temperature is the enthalpy of formation for that species plus the sensible enthalpy that is required to preheat the, heat up the following species, right? And this basically can be calculated as your integration of Cp times dT. So Cp is the specific heat for that particular species, and dT is the change in temperature that you are going. So sometimes Cp is a function of the temperature, so that is why you have to integrate it. You cannot just directly multiply the dT. So these values for the species are available online. So there are databases, standard databases that you can look at. So I'll just show you quickly. So these are NIST, JANAF databases, thermochemical databases that you can use to find the species details, right? So if you just Google, okay, so you get this kind of a table, and you can enter the particular species. For example, let's look at methane, CH4. So you get that, and when you click and submit. Okay, so now this gives us the Cp values as a function of temperature, right? It also gives us this enthalpy of formation at different temperatures. Standard enthalpy of formation is at reference conditions. So reference conditions is temperature 298.15, okay, and pressure of 1 atmosphere, right? So you have standard enthalpy of formation as for methane, your standard enthalpy of formation is minus 74.873 kilojoules per mole, right? So these are molar basis. And you can use this table to find out your enthalpies at different temperatures as well, okay? Alright, so now that we know how to understand what is the energy content in a particular species, we want to apply that to a reaction system. So if you, let's say you have a standard reaction that is A plus B, two reactants giving you product C plus B. Okay, you want to find out what is the enthalpy of reaction, how much energy will get released if you have that chemical reaction. So the assumption to calculate these are, like, assume that you have a steady flow reactor. So you have reactant centering at standard reference conditions. So what is standard reference condition? Temperature is 298.15 and pressure is 1 atmosphere, right? So they are entering at that condition, so it is reacting within this vessel, right? So it is completely reacting to produce C plus T as products, and the products are exiting at standard reference conditions, right? So the product's temperature is also 298.15 and pressure is 1 atmosphere pressure. Okay, so this is a stoichiometric mixture, so all the reactants are getting completely burnt, and the reactants and products basically enter and exit at standard state conditions. So if I apply that, then the enthalpy of reaction, delta HR for this is nothing but the enthalpy of the products minus enthalpy of the reactants. Alright, so in this case products enthalpy is enthalpy of C plus enthalpy of D minus enthalpy of A plus B. Okay. So just as a question, so if this is an exothermic reaction, like for example combustion reactions are exothermic in nature, so what is going to be the value of enthalpy of reaction? Is it going to be positive or negative? Positive? How many are positive? Please raise hand. 1. How many are negative? How many negative? 1 negative. How many unsure? Okay, unsure. Fine. So what happens is, let's analyze a bit. Okay, so this is an exothermic reaction, means it is releasing heat as you go through this chemical reaction process, right? So now this guy has some amount of energy in it. It is getting converted to C plus V and it is releasing the energy. So if you apply conservation of energy, what does it say? There is no additional energy going in. So if this has 100 units of energy and releasing 30 units of energy as heat, what is the energy content of C plus D? 70, right? So the enthalpy of this guy is lower than the reactants, right? So in an exothermic reaction, the enthalpy of products are usually lower than the enthalpy of, not usually, always lower than the enthalpy of the reactants. Okay, at standard conditions, standard reference conditions, that is also very important. Okay. So typically the delta HR value you will always see for exothermic reactions as negative. Okay, for endothermic reactions it is opposite, it will be positive. Okay, so that is that, and heat of combustion is amount of heat that is released, that is nothing but the minus of delta HR. Okay, it is also known as the heating value of the fuel. Right, you might see higher heating value, lower heating value that is labeled on the fuel. So that is basically calculated using this process. Now you can have, there are two distinctions, you can name it as higher heating value or lower heating value, and these are basically based on the phase of water that you are considering. So if you have this reaction, okay, methane stoichiometrically reacting with air, so you have water coming out. Now at standard conditions you can assume water to be in the gas phase or the liquid phase. So depending on that, the enthalpy of this water is going to be different, right? So depending on the phase of water that you are taking, so you will have a higher heating value assuming that all the water in the products has condensed to liquid, right? Condensed to liquid means it has lost heat and then it has gone from vapor phase to liquid phase, right? So that will give you a higher heating value, and lower heating value is, so none of the water in the products has condensed, so they are in the vapor phase, right? So it has not lost that enthalpy of condensation. Okay. So now if you want to do a quick calculation of this enthalpy of reactions, so for methane air mixture, so these are the products. So these are the enthalpy of formation values that we got from the, you can get from the JANAF NIST database. Alright, so this is for methane, this is for water in the vapor phase, this is for CO2. Okay, anything that we are missing here? Right? We don't have the enthalpy of formation, the enthalpy is for O2, N2. It is, why is that? Let's have a look at that. So let's check in the online database what it shows. So one of the species was O2, right? So oxygen. So if you look at that, You see that at standard reference conditions 298 Kelvin, the enthalpy of formation of O2 is 0. Similarly, if you go for N2, it will be also 0. Okay. So basically what we are saying is, if you consider any element, okay, element is like probably let's say oxygen, nitrogen atom, okay. So oxygen, nitrogen, hydrogen, okay. So in the elemental state, like a species consisting of single element, okay, how does it exist naturally? So oxygen atom does not exist in nature, right? It exists as O2 molecule, right? Nitrogen exists as N2 molecule. Hydrogen exists as hydrogen molecule, okay. So the energy that you need to form these molecules at standard reference conditions is basically 0, okay. So that we treat that as a reference value. So the enthalpy of formation of element like naturally occurring elemental forms, that is O2, N2, H2, is basically 0. Okay, so that is why in this equation, like if you start to calculate enthalpy of formation at reference conditions, these are 0. Okay, but CH4, it is a combination of two different elements, right? So you have to bring these elements, and that you need to have some process that forms those molecular bonds, right? So some energy involvement is there. Okay, so enthalpy of formation of these species are 0, right? Any other species that you can think of that is elemental and occurring naturally?
Molecule form.
Molecular atom, anything? Carbon as a gas?
As an element.
As an element it occurs as soot, yes, but not as an atom. It is usually connected with a chain of atoms, right? So you have noble gases, inert gases, right? They are also occurring elemental state, and they don't react with any other. So all those enthalpy formations will be 0. Okay, but if you heat those things, so if you heat oxygen to 500 Kelvin, then it is going to have some enthalpy, right? The sensible enthalpy component is going to come in. Okay, so this is how you can calculate. So anyone calculated what is the enthalpy of reaction of this? Alright, so we have things going in at standard reference conditions, and CO2, water vapor, and nitrogen coming out at standard reference conditions. Okay, I will leave it as a task. I can show, there are some tools, online tools that you can use to easily calculate, but these are again something that you can also do it by hand. Okay. The next concept is something that we call as adiabatic flame temperature. Alright, so when a flame is burning, it is having some kind of a exothermic reaction that is taking place. So it is releasing heat, and it is heating up the nearby local volume, right? So many flames that you will see are basically housed inside some kind of a geometry or a structure. So this is basically a flameless combustor, again a research facility, and this is again like in a furnace. The flame is basically housed in some kind of a structure. Okay. Now the flame temperatures can be very, very high, and it can affect the integrity of the structure, right? So typically, what kind of temperatures do you expect a flame to have? 700 degrees Celsius. 700. Anyone else? Any other guesses? What is the highest temperature that a flame front will have? 3000? 1200 degrees Celsius. Okay. Now, even if these are, let's say these values are correct, the integrity of even these metallic components, they will basically start yielding at those temperatures if you run it for long time, right? So it can have those kind of thermal stresses developed, and it will lead to failure. So it basically hampers the durability of these kind of reactors. Okay. So that is one of the reasons why you need to know what kind of temperatures are you going to expect at the flame front, so that you can employ effective heat management. Okay. And also in terms of emissions, so at high temperatures you start to get high amount of NOx emissions. This is particularly very important in engines and combustors. Okay, so for these reasons, we want to calculate at least it may not be accurate, but we want to calculate the theoretical maximum possible flame temperature that is coming out. All right. So in that case, so what that means is, so how do you have the maximum possible flame temperature? You assume that so a reaction is going on in a particular volume, and that is not losing heat to the environment. So it is an adiabatic system. All the heat that is being generated is being absorbed by the gases itself. Okay, so if you have heat losses, then your flame temperatures can come down. So adiabatic flame temperatures will basically give you the theoretical maximum possible flame temperature limit for a given fuel air composition. So what we want to do is, so let's assume it to be a constant pressure system. So you have some methane and air mixture, okay, sitting inside a volume, and you supply, it is homogeneously mixed, it is flammable, and you supply the required ignition energy to it. So it starts combusting. So once it starts to combust, what is going to happen? So if it is a constant pressure system, so this piston is going to expand. So the volume is going to expand as the combustion happens, right? So it goes from state 1 to state 2, okay? Now we are assuming, if you want to calculate adiabatic flame temperatures, we are assuming that there is no heat loss happening through the walls or through the piston. Okay, so now applying the first law of thermodynamics to this system, what we have is going from state 1 to state 2, the change in total energy of the system as you go from state 1 to state 2 should be balanced by the heat that is being added to the system during this change minus the work that is being done by the system. Okay, so in this case the work is being done in order to expand the volume. Okay, so this is straight away first law of thermodynamics, and if you apply those, then basically the change in total energy is E2 minus E1, so 1 and 2 are the states, state 1 and state 2, minus any heat that is being added, minus the work done, that is pressure times PV2 minus V1. So this total energy of the system has three components. One is it could have some potential energy, it could have some kinetic energy if the whole mass is moving, and some internal energy that is basically related to molecular vibrations that are taking place at molecular scale, right? So the summation of these three gives you the total stored energy minus potential energy, kinetic energy, and U1 at state 1. They should be equal to the any heat addition that is taking place minus the work done in expanding the system. Okay, so in most of the systems, the change in potential energy or kinetic energy is negligible, so you can neglect those. So P2 E2 minus P1 PE1, sorry, PE2 minus PE1 basically cancels out, and similarly kinetic energy cancels out. So what you get is P2V2 plus U2 minus PV2 plus U2 minus PV1 plus U1 equals to the heat that is being added during the system, during the change of process. So enthalpy is nothing but, as we discussed, the internal energy plus the work that is done to expand the to find a volume for itself, right? The flow work. So this is nothing but enthalpy of state 2 and minus enthalpy of state 1, and that is equal to your heat that is being added during the process, right? So for an adiabatic case, the heat that will be added is 0. So this goes to 0. So basically the process of 1 to 2 is a constant enthalpy process, constant enthalpy, constant pressure process, right? So for constant pressure adiabatic systems, you have enthalpy of reactant should be equal to the enthalpy of products. Okay. Any doubts? Any questions here? Okay. So now that we know for a constant pressure system, the total enthalpy of reactants and total enthalpy of products are equal, and we know how to write enthalpy expressions, right? So now if you want to analyze this combustion reaction, methane plus air, equivalence ratio 1 gives CO2 plus 2H2 plus 7.5 to nitrogen. So what you want to do is you want to find have the expression for enthalpy of products H2 and enthalpy of reactants and equate them. Okay. What is unknown here? We don't know what is the temperature of the products. That is what that is the unknown that we are trying to solve for. All right. So let's first write the expression for enthalpy of products. That is going to be equal to, so you have 1 mole of CO2 times the specific enthalpy for carbon dioxide we don't know the temperature, so we just name it as T adiabatic. That is what we are trying to solve for. Plus 2 times of, so you have 2 moles, 2 times of specific enthalpy of water, plus 7.52 is the number of moles of nitrogen. So now that we have this expression, now this total enthalpy of carbon dioxide at T adiabatic is nothing but the enthalpy of formation, that is at standard reference conditions, plus the sensible enthalpy term, right? That CPDT term that you need to basically raise the temperature of carbon dioxide from 298 Kelvin to the adiabatic flame temperature. Okay, and this is something that we don't know. Similarly, we can write the enthalpy of water vapor and enthalpy of nitrogen expressions, right? So this is one expression that we get. And similarly, we want to write the expression for the reactant side. Okay. So you will get enthalpy of methane as standard enthalpy of formation plus the sensible enthalpy T1. We have not specified what is the temperature of the fuel and air in this case. So we keep it as T1, and similarly for the O2 and nitrogen. So in this case, what happens? So the enthalpy of formation of nitrogen is 0. Enthalpy of formation of nitrogen is 0, but there could be sensible enthalpy term that is hanging around. Alright. So let's do a calculation for assuming T1 to be 298 Kelvin, then these terms basically go away. So assuming that the initial temperature for the fuel air mixture is ambient, 298 Kelvin, these sensible enthalpy terms also go away. So now what we have is, when we equate the expression for enthalpy of products and reactants, we have one unknown with us, that is T adiabatic, that is hanging around. So when you solve for that, you basically get an estimate of the adiabatic flame temperature. Okay, so let's keep in mind, so for adiabatic flame temperature, you have at constant pressure, these are constant pressure systems, so you have constant pressure process and constant enthalpy process. Okay, so we can do these calculations in hand, but there are also open source tools that is available online to estimate these. So we can quickly have a look at that. So there are softwares like open source tools like Stangen. So these are tools that are available freely online, which you can use to estimate what is the flame temperature. So one of them is this one. Okay. So here what we have to specify is, okay, so what we can do is we can enter our input conditions and get a value of the flame temperatures that we are trying to calculate. So for our case, what is the starting temperature for us? Methane and oxygen, methane and air, 298 Kelvin, and we are working at 1 atmosphere. 1 atmosphere. And so this is an iterative process, so it is asking for us estimated equilibrium temperature. So equilibrium temperature means what is the final state? Any guesses? So 700 degrees Celsius is someone said, right? So we can accordingly enter, so around 1000 Kelvin. Then what should be our good guess for equilibrium pressure? 1 atmosphere, because this is a constant pressure process that we are trying to see. So once we set these initial conditions and our guesses for the solver, we would go to calculation constraints, right? So in this case, you have these different kinds of processes that is given to you. So for calculating adiabatic flame temperature, constant pressure, what should be our thing? We should select this constant pressure and enthalpy, right? So if you click this, so this is the one that we want to solve it for. Just reminding, if you want to calculate the enthalpy of reaction, what kind of process should we have? Enthalpy of reaction was your fuel and oxidizer is going at standard reference conditions, it is coming out at standard reference conditions. So what is that process?
Constant pressure and temperature.
Okay, constant temperature and pressure, because yeah, the reference conditions are maintained, right? So you select this constant pressure and temperature, and you can simulate these various processes. Okay, so now here what we want to do is we want to specify the elements that are involved. So in this methane oxygen oxidizer reaction, what are the various elements? So we have carbon, we have hydrogen, nitrogen is also existing in air, and oxygen. Okay, these are elements. And now what we have to do is we have to specify what is the reactant mixture fraction, right? Or the reactant mole fractions. So in our reactants we had methane, right? So we have CH4 and it was 1 mole, right? So accordingly O2, how many moles for 5-1? 2 moles, and then nitrogen is 7.52. Right, so these are our reactant mixture mole fractions that we can enter. And after this, any additional species that were not there in the reactants but could be there as products, right? So those are CO2. CO2 is something additional that is a product, and H2O, water vapor that can form. Okay, for now let's consider these. There could be additional products, but we're not considering dissociation reactions and things like that. So once we do that, we ask it to calculate. So it probably takes a few seconds. Okay, done. So let's zoom in. Okay. So initial state and equilibrium state. So you look at the pressure and temperature. So the pressure is constant. So that is 1 atmosphere, 1 atmosphere. What happens to the temperature? So you are giving the fuel air mixture at 298 Kelvin, and the temperature of the final temperature that you see in this process, what is it? 2327, right, around 2300 Kelvin. So that is the adiabatic flame temperature that you basically will get when you are burning methane with air at stoichiometric condition. Okay, so the flame temperatures are way higher than what we expect. So what we measure is exhaust gases, that is you have a lot of heat losses, heat transfer to the surroundings, and after that probably you are measuring 700, 1200 degrees Celsius. But at the flame front, right, your temperatures are at 2300 Kelvin, 2200 Kelvin for typical hydrocarbon fuels. Okay, so that is, so your combustors or the structures, if it is getting in touch with these kind of flame fronts, so you can imagine the amount of heat transfer that is taking place, because these are at 2300 Kelvin and your temperature, your structures might be at 300 Kelvin ambient condition. So a lot of heat loss, heat transfer will take place. Alright, so that is one. And on the bottom it gives us an idea about what is going to be the initial composition and the final composition as products, what you find out. So in your initial composition we had given, so this calculates the mole fractions, and in the final we basically see that methane and oxygen mole fractions are very, very low. That means it is almost completely consumed in this case. And you also get the, what are the product species. So water vapor, CO2 and nitrogen, you can find out what is the mole fraction and mass fraction out of it. Alright. So this is a very useful online tool where you can use it to understand different types of fuel and different types of conditions. Okay. So probably 5 more minutes and then we'll stop. So this is a process in which we estimated adiabatic flame temperatures at pressure, 1 atmospheric pressure, and temperature, initial temperature was around 298 Kelvin, and the mixture ratio was stoichiometric mixture, right, 1 mole of methane and stoichiometric amount of air. So what happens if we change it? So like it does not have to be a same equivalence ratio mixture, right? It could be lean or rich mixture. So for that, so let's try to go for a rich mixture. So in that case you have excess fuel as compared to the stoichiometric composition, right? So in that case what we can simply do is, instead of 1 mole of methane we can have 2 moles of methane, okay, and maintaining the air composition same. So let's do this. And in products of combustion, do we need to add anything else? Methane is already there in the reactant, so it will treat it. Okay, but because of incomplete combustion, there might be carbon monoxide that is coming out, right? So that could be a good guess of some additional species that we want to consider, right? So let's put carbon monoxide over there, and again, so all the other settings are same, constant pressure and enthalpy, and let's calculate again. So now what we are doing is calculating for a richer mixture, considering some additional products that are there. So what happens to the temperature? So our first thing is this is also the adiabatic flame temperature, right? But for a rich mixture, right? For a rich mixture, what is the adiabatic flame temperature? It is around 1840 Kelvin. So what you see is the temperature has gone down, right? When you have a rich mixture. And let's look at the composition, product composition. So in product composition, you now have some amount of methane hanging around. So this is 0.05 mole fraction. It's not non-negligible. So initially we had 0.17. Oh, sorry. Let's look at mass fractions. So 0.1 mass fraction, and it still is there around 0.035 mass fraction, which means that there is some amount of methane that is still existing in the products. And the oxygen mass fractions are negligible. So these are 10 power minus 14. So these are very small values. And now you can also see that you have some carbon monoxide that is also coming out as products of combustion. Okay. So there are two things that we found out. So when you have rich mixture, this can estimate what is the final composition of your exhaust gas that is coming out when you have rich or lean mixtures. And one thing that we noticed is the equivalence ratio when we changed it from stoichiometric to rich, the temperature dropped. The adiabatic flame temperature dropped. So why is that? Yes. Due to incomplete combustion. Okay. But the amount of we increased the amount of fuel.
But we cannot give it in equal proportion. There is more fuel, but there is less oxygen.
Okay.
Therefore, it will not combine completely. And there's some amount of yet.
Okay. So let's try to understand that. Okay. So in our first instance, we had 1 CH4, right? 1 mole of CH4 with us, and then we have 2 moles of O2 and 7.52 moles of nitrogen, and this gave us a temperature of around, how much was this? 2300 Kelvin, right? And in the second case, we have two moles of methane, and this gives us somewhere around 1800 Kelvin, okay, lower temperature. So in this case, what is the deficient species? The deficient species is air, right? So this much amount of air is still going to burn, let's say 1 mole of methane. So you are burning, in this case also you are burning 1 mole of methane. Okay, so you have some additional methane that is not burning. But in this case, in the first case you are burning 1 mole of methane, and in the second case also you are burning 1 mole of methane. Right, so the energy that you are getting out should be the same. Right? Incomplete combustion because you have some residual methane. But still the amount of methane that you are burning is still the same in both the cases. So energy output is same. So why is temperature going down?
CH4 is converting to CO.
CH4 is, yeah, so you have some additional species, CO, some CH4 is remaining, right? Yes, so one of you have some of these additional species that are not taking part in the reaction or partially taking part in the reaction, and they are existing in the product side. So what happens is, when you burn completely 1 mole of methane with air, you are producing, let's say let's take a example, let's say you are producing 100 units of energy, and that unit of energy is going into raising the temperature of the products, right? Now in this case, so you are burning the same amount, so you will produce 100 units of energy, And now in products you have some additional amount of methane that is hanging around, right? So that is additional mass that is hanging around in the on the product side, right? So now along with water vapor, nitrogen, CO2, you have these additional components, additional mass that will also absorb the heat. Yes, so mCp delta T, when you do it, you have some added mass, Cp is there, so dt has to go down to maintain the same energy. Right, so the temperature will basically go down because you have some additional unburnt species or unreacted species hanging in the product side. Okay, so this will happen for rich mixtures as well as on the other end. If you go for lean mixtures, you have excess air, so that those excess air will be hanging in the product side. So that will also lead to a reduction in temperatures, right?
Reduction of the temperature will not continue.
So it is at a steady state, the final.
Normally temperature, it reaches the temperature.
Yes.
The reaction continues. Instead of the CO2, CO forms. Moment it gets any external air, normally we call it flashover, when we break the windows and something.
Yes, yes.
It happens. The temperature will not come down. It may be steady, but it will not continuously come.
Yes, in those, yes,
So how
correct.
can I explain that thing?
So,
Understand.
so in this case, we have, there are some assumptions.
We might conclude it it is decreasing.
Yes.
It is not decreasing actually.
So these are theoretical maximum temperature limits. In real cases, you will have heat losses which are also governing the temperature. So the maximum temperature that you get is assuming things like there is no heat interaction, right? So these heat losses are zero, heat losses or heat addition, and also there is no additional air. So the oxidizer interaction is not happening. So what you are supplying is just the fuel and oxidizer through this port, which is a steady flow. So
Whatever continues, we are not providing the fuel here.
No, here it is not actually reducing. It won't go to that of say 2300 Kelvin. It will remain as 1800 Kelvin. So it won't be.
It will not come
I mean,
down.
The mass is now and the product side is more. So that's why it won't be taking up the temperature.
Exactly.
Sure,
But
that
it will
will.
not come down.
Yeah.
So it's like
steady also.
It won't come down, but it will remain 1800. It won't go up rather.
right, yes.
So that is.
So it is like boiling water, not heating water 1 liter versus 20 liters with the same amount of heat. 20 liters will get to a lower temperature because you have that added mass. Okay. So now if you just look at trends of adiabatic flame temperature versus equivalence ratio, stoichiometric lean and rich mixtures, you can see that the flame temperatures typically peak somewhere around 5 equals to 1, 5 equals to 1.1, and that is happening because of specific heat variations with temperature also. But in general, what you get is towards lean and towards rich mixtures, you get lower adiabatic flame temperatures. At stoichiometric mixtures, you have typical stoichiometrics, or slightly rich mixtures, you have the peak temperatures, right? So on the other hand, also like in the oxidizer, if you use air as an oxidizer, that has nitrogen with it, versus if you use pure oxygen as oxidizer, so only O2, so you are no longer having this added mass also, right? So this is not, temperatures can even go when you are looking at oxycombustion. So you can look at methane. So here as oxidizer, you get temperature 100 Kelvin. If you replace it with oxygen, just pure oxygen, you get around 3900 Kelvin, right? So okay, so we'll stop with this. There are several open source tools that you can Google and use the software. Okay, thank you.